So today and the beginning of next week, we will complete the first part of our journey. And you're probably bewildered because this is some kind of physics course and it's all drawings and God knows what. And it goes against the training of a physicist. So what we did in the first part of the course is we tried to popularize some geometry. And in a sense it's an ode to curiosity, because all the ideas which are important today were just done out of curiosity. Nothing that we do was NSF or NIH sponsored directed research. And in the long run, this is the amazing stuff. So the fundamental idea that underpins it all is that after a long time between Leibniz and Poincare, the focus was on being a virtuoso in analytic solutions of very complicated integrals, typically in celestial mechanics and fluid mechanics and electromagnetism, etc. And that's all they could do. I mean, it was totally amazing. It was all they could do. And Poincare was a person who understood that you must have a feeling for qualitative theory of differential equations of flows. And that's what we've been doing up to now and do it also today and a little bit later. So what I'm presenting is a vision of Poincare and Smale in the 60s. It's a puzzle because it looks like pictures. It looks useless to you. I mean, drawings and cartoons, and you're working people, you don't have use for it. But calculations at the machine precision. And what's happened between them and us is that they developed a qualitative theory, but we can actually implement it. We are lucky to be here in time where you have a tool, and that's just a tool, that says that if I understand the qualitative theory of dynamics of how things evolve in time, and I can actually compute this. So these pictures are extremely powerful. I mean, when you implement them, they're all to machine precision, they give predictions. Often you don't care about machine precision, but if you apply this, I won't cover this in this course because there will be a 2-semester course in quantum mechanics and quantum field theory. When you use these ideas, you compute spectra of helia, so, things that are measured with very, very high accuracy. Here we insist on precision when we implement this because the theory turns out when you have simple rules, simple laws, how things should behave, but long-time behavior is complicated, the way that we will understand it will in terms of classifying invariant structures that characterize the thing that looks very complicated. Our intuition is that you have a very simple, like we have a parabola, or even the tent map I showed last day. So how complicated can that be? So there must be some intelligent way of using the information that the law is simple and projecting that information beyond the horizon, which is called a prune of time, but beyond the horizon where numerical work could get you without thinking. So our strategy was so far to define another picture, define all possible things, enumerate them, so that's called state space. And unless you do that, you can't do anything. And then describe the law which tells us how things move around the state space. So that's the definition of dynamics in this course. There are more refined definitions, but this should work for us. And we did this by first looking at trajectories. An important thing is that we discovered there were sets of invariant trajectories. There were equilibria, and no matter how complicated the motion is, the mathematical solution, which is equilibrium, it's not complicated at all, that we found that there were recurrent motions, which were a little bit like what people always hoped to find when they were doing analytic integrals. in celestial mechanics, something that you can describe in a very simple way, motion as motion on the circles. But they turn out to be unstable, isolated, and as you will see, there's a very large number of them, infinite number. So these are periodic orbits. Then there are other structures. And importance of this object is that they have temporal dynamics, even though they are invariant as a sets. So they sit in this space and just sit in some part of the subspace, and they don't know what's happening everywhere else. They start capturing the temporal evolution because the points are marching along them. And there is a list that is very short in practice because we actually don't know how to control most of these objects. By now we have mastered basically equilibrium, periodic orbits, and some tora, but the general classification of this motion eludes us. So that was the first thing. What happens to point? What happens to a mathematically infinitely precise thing? But there are no points for many reasons. There are only fuzzy objects, which is our best specification. And that could be because we have finite numerical precision, or we don't understand the law. So we have approximate law, like we have Newton's equations instead of the correct ones. Or we live in a world that perturbations that we don't control. So something happens, Professor Goldman exits the lab and the acoustic waves propagate in here, and there is no control of it. So the things are really not sharp, and that's totally different. So what happens, the moment that happens, the world, we have gone from idealized world of determinism to statistical mechanics, which is fully deterministic. The laws are deterministic, but the way thinking about it is very different. You have to start thinking about distributions. And that'll be the second part of this course. But what we found was that it was very useful to understand transverse behaviors. And that led to an unfortunate, but either very ugly or very beautiful, depending how you feel about diversion in thinking about symmetries. So there were here symmetries. So it often happens that laws that we look at, the phenomena they observe, they look like in kaleidoscope. There's something like that, and there is something like that, there is something like that. And that's beautiful, but it turns out it interferes with understanding. I made a little digression, which required actually writing formulas. I apologize. And this is absolutely necessary because one has to understand the global dynamics of what happens, at least to neighborhoods, bunches of co-traveling fellow travelers. It's absolutely essential to go into Poincare section plus slice. And in that world, all the motions that had to do with marginal directions in which things don't really change, so everybody who belongs to a marginal manifold is just different placement of the same shape, and start discussing what happens in this transverse space. That is totally necessary already on the level of this thing. And what we have done now for a week, and I'll finish doing today, is that once we understand this, we can start in a very precise way with the local properties of the flows and find the global properties. And no night fishing is needed. This can be done by thinking your problem through. It's not easy, but the other thing just doesn't work. That enables us now to think of the state space, which was in the beginning just lots of points connected in some very obscure way, to think of it as a smaller space, and here is a smaller space which you can write in various ways, but basically what you do is you identify all physically same things under the symmetry group, which could be discrete, continuous, whatever, but it's just a group of all coordinate changes that identify objects which are physically the same, have the same shape or same energy or whatever. All properties are same, modulo coordinate transformation, and actually also want to quotient out the time. You did that by Poincare sections, and it's this space, which is not much smaller than the original space. So original space can be any dimension. If you're looking at systems described by partial differential equation, original space is infinite dimension because it's function space. It's every slightly different function is a point in it. Or if you do it the way we do this as a set of coupled ODEs, it's lots of ordinary differential equations coupled, Fourier modes coupled by nonlinear terms, etc. And this space now gets reduced only by one dimension for time and few dimensions for symmetry group, depending on the symmetry group is. But what's captured now in this space is the way that you can leave a neighborhood of one fixed point or one periodic orbit or one relative periodic orbit or one torus or God knows what, but you have quotiented all that stuff out. How you actually get from there to some other neighborhood, which has its own invariant thing. And there are things that I'll try to explain today called homoclinic connections, etc. But there are invariant ways to get from here to there. And the power of that description is that it's invariant. No matter who does it, where does it, under what coordinates does it, you'll get the same result. And you'll capture the essence of the dynamics in this way. So I'll just fill in a few more details. It's work, and there is no way out of it because nonlinear dynamics is not simple. But it's systematic. So if you have a problem, you'll have to work in a different way on every problem. And maybe you'll discover lots of exciting things that are missing from this exposition. But it's a way to do this. If you find out that you're in a situation where everything looks unstable locally, that doesn't mean that the world globally is unstable. It just means that individual trajectories cannot be predicted with accuracy beyond some time horizon. But it turns out, which will be obvious in second part of the course, that the thing that you really have to think about, which is likelihoods of being transported from someplace to someplace by dynamics, it turns out to be very robust. So while things fall apart on one point level, they actually become very stable on the level of densities of points. There will be a dual picture which makes it actually very easy to describe long-time behaviors once you understand what they are. And the strategy that we started explaining last time is to explore how is it that you leave a neighborhood of one of your invariant solutions